creating a slope or setting the slopes. Why you need to set the slopes? Because slopes are actually considered as your physical constraints for the optimization that you are going to run later. Because you need to basically constrain your pit based on these physical boundaries that you have in terms of the angle, and then say go and do any kind of optimization you want to do based on this constraint, this physical constraints that you have. So if you don't see this branch from here, so and there is nothing appeared here, you can easily go to your block model, right click, add slope set. So if you didn't find it, you just need to go to the kind of the other knot, and then you select the right click, add slope set. But we have it here. Now, again, I could put different descriptions, depending on what kind of methods I'm going to use for assigning these slope sets. There are different ways of defining slopes, either by rectangular slope region, by rock type, by zoning or profiling. So when you go with rectangular slope region, and if I click go to profiles, you need to basically identify in your block model different rectangular areas or zones in your block model that you want to assign different slope angle to those specific regions. You could either do this in your initial block model before importing it to Whittle, or if you want to do it here, so you need to basically play with this profiles and make basically new regions and assign different profiles to them. As you can see, we only have here one profile, and this profile shows 45-degree slope angle for all the areas of the pit. Now, I can add other profiles. For example, profile number 2, I want to be 48 degree, okay? So let's assume a scenario where you basically the upper part of the pit is in a highly weathered rock, okay? Let's say for 40 meter, and then after 40 meter, the rock becomes less weathered. It's becoming a kind of bedrock, a competent rock. So we want to assign different profiles to them. So for the first 4 benches, I'm going with a profile of 45 degree, and for the remaining of the pit, I'm going to assign a higher slope angle. If this is the scenario, so you need to just go and create these 2 different regions in your block model. So how I should basically create those regions by just looking at the Z elevations of the block model. So I will say, so the 44 represent the surface, okay, of the block model. So I would say from, let's say 40 to 44, okay, assign the profile number 1, and then create a new region where all this information are exactly the same, like the min X, max X, min Y, and max Y, but here it's going to be, what, 39 to, sorry, it's 1 to 39. Because otherwise there will be an overlap, right, between the 2. So here I want to use a different profile number 2. So the first 4 benches will have a profile of 45 degrees slope angle, and the other parts below this, below the 40 meter, it's going to be the profile number 2, 48 degree. I can actually change the profile also based on the azimuth of the slope, because we know that different area of the pit might basically have a different slope angle, depending on the orientation of the discontinuities, if they are favorable or unfavorable with respect to the slope angle, right? So you can do this easily by going here. Let's say I want in profile 2, I want to assign different slope angle to different area of the pit. How? Let's assume that this is your pit, okay, and this is north. Now, if you assume that you are in the middle of the pit, and this is the slope of north wall, this is the slope of the east wall, the south wall, and the west wall, I can assign different slope angle to each one of these walls. How? By changing the azimuth or bearing angle here, I could assign a different angle to each one of those bearing. So for this one, if I look at it from the middle, the bearing angle here is 0, or azimuth is 0. So I could assign, that's 48 degree to bearing angle 0. Then I could add more here, okay? So I could say for 90 degree, which is this slope, this wall, go and assign a slope angle of 50 degree, okay, because the rock is better. To the south wall, which is 180 degree, go and assign a lower slope angle, 45 degree, because there is a joint that is unfavorable with respect to the wall. And for the west wall, go and assign again a higher value of 47 degrees. Okay? This is going to change gradually the slope angle between the south wall and the west wall, so that when you are in the west wall, it gives you exactly the angle that you have entered. Another way of doing this is that you could actually go and say, I want from this bearing to this bearing to be exactly this number. So if you want, you have a wall that starts from a point to another point, so and you want to assign an exactly this specific slope angle, so you could say 220 to 220, 48 degree, 320 also 48 degrees. So basically between 220 to 320 is going to assign exactly the angle that you have entered. Okay, so you could basically fix it for a certain range. Otherwise, it's going to gradually increase in between those numbers.
If you were to fix it with a certain range on this, how would you like plug it into the bearing?
Okay, so what you could do, if I do this, I would say from 330 to 30 degree. So 300, I want to change, so let me delete this guys. 0 is, so let's put it 330, 48 degree, and then 40 degree, again 45. Sorry, 48. So what does it mean here? It means that between 330 to 45, with respect to the north, it's going to be 48 degree. It's not going to change it, okay? Because you have one wall, okay? And then I can add here, so from, again, let's put, so this is 40, again, now I will put 120, 45 degree, and 220, 45 degree. So between 120 and 220 is going to be 45. Yes?
So does that mean if we set it like that, the range from 40 to 120 will gradually slope?
Increase, yes. Okay. Will gradually increase. Correct.
Or decrease. Okay.
Sorry, decrease in this case, yeah. From 48 to 45. but it's gonna be constant between those numbers that you have assigned, like between 120 to 220, or between 330 to 40. So here I'm going to make it a simple case, so don't want to. So what we had here was 0 and 48 degrees, okay? So we assign a profile 2 to this lower levels and a profile 1 to the upper levels, okay? So this is one way of doing this. The other way is by going and selecting rock types. So if you have different rock types on different walls of your pit, you could basically assign different profiles to them. For example, as you can see here, you have all these different rock types. And if I know, for example, this rock type is representing my hanging wall, and I want to assign a specific slope angle to this rock type, so then I would go with this option, which gives me the rock types, and then I can assign specific slope angle to that rock type. Okay, so as you can see, I can assign different profiles to different rock types, like this. I can still go and have these profiles changing based on the orientation for each rock type. For example, if a rock type covers east and north of your pit, so then you could have a different profile for the same rock type, but for north wall and east wall, a different angle, right? So let's go back and use this. The two other options are where you already identified the zones in your initial block model, and you have assigned a specific name or number to those zones. For example, zone 1, zone 2, zone 3, and then when you go with this option and you click on profile, as you can see, there will be like the rock types, but instead of rock types, there are zones here. For example, you have hanging wall, foot wall, or weathered, etc., and then you want to have different profiles for these zones. We don't have it here, so we go back, we go with the simple case, and we select here. Every time when you did you entered the parameters, you click on accept, okay, and then you are allowed to basically run it. If you want to make sure that your numbers are correct, so you could also check the data. So it's gonna look at the data, and so valid data. So now you could start running it.
Couldn't you just run everything in one go? Like set everything?
Yes, you can, but you prefer to go one by one because you want to check if there is any error. You want to check where was this error. Okay?
But wouldn't the check data button do that for you?
Yes, it is. It's possible, but I've always done, step by step. But you could absolutely, you could go and create all this, input parameters, and then run them all together. It's not a problem. So this is the step for assigning or setting the slopes. Now, the next node we have here is the pitch shell generation. Okay, so it's going to ask you for the input parameters, and the input parameters are economic or cost and prices that you need to enter here, and all those technical parameters like recovery or dilutions and those kind of things. So here, why we need this parameters? We need these parameters in order to be able to generate the pitch shells. So Whittle is using Lurch-Grossman algorithm. You probably remember the Lurch-Grossman algorithm in surface mining course and how the Lurch-Grossman algorithm works, right? Hopefully. But if you don't know, it's okay because it still is going to run and it's going to generate the pitch shells for you. But so what you need here is entering this different parameters in terms of the input data that you need in order to be able to generate these pitch shells for you. One of the things that you need is the cost of mining and processing. So the cost of mining, you need to know what is the mining reference cost. So the mining or reference mining cost is the cost of extracting a unit of weight of rock. It's going to be dollar per ton or dollar per pound or whatever you are using in terms of the unit. Here we go with ton. So you put this number here. Let's put something like $2, okay, or $2.4, for example. So this is the cost of what? Cost of drilling, blasting, loading, and hauling, right? And you are assigning this number to all the block mold, blocks that you have in the block mold. The next parameter is what is the mining recovery. So what's the mining recovery?
Actually, how much rock you're taking out from the ground.
Not the rock, but the mineralization. So you have a mineralization zone, right? But you cannot always extract all those mineralized zones, right? So there should be some of those mineralized zones will remain in place because of all those challenges that you have in extract. So let's put it 90%, 0.9. Then here you have another parameter which is dilution. Okay, dilution here is what? Is all those waste that will come with the ore and basically goes to the mill or goes to the processing plant. Okay, so this is something that you don't want, but it's gonna add to your capacity, to your mining capacity. So it's gonna be something more than one. Okay, so it's gonna be 1 point. If it's 10%, I will put 1.1. If it's 5%, I will put 1.05. Right? Because it's something that's gonna add to your mining capacity. Correct? Now, as you can see here, we have something called block mining cost adjustment factor. So we know that the mining cost is not going to be constant for all these blocks that you have in your block mold. Why? As you go deeper in an open pit mine, the hauling cost specifically and also the loading cost is going to increase. Why? For example, if you want to displace the shovel from one place to another, okay, it's going to take more time. So the cost is going to be much higher than when the shovel is working on the surface. The same thing for the hauling, right? So the hauling cost of material as you go down is going to increase. Now, how I can adjust this basically cost in my block mold to be able to reflect this? There are possibilities that you could put it as a function here. So you could go and calculate and put the function. So you could say, for example, I want to assign a specific factor to my reference mining cost that as I go from, let's say, bench number 4 and down, at each bench I'm going down, assign a higher coefficient number to my reference cost so that it could reflect in my mining cost. Basically, the mining cost, you put it there, is the mining cost of the first few benches you have on the top, and as you go down, it's gonna increase by bench. Or, let's say if you have, so this is all this, you could do it by looking at all these variables, looking at the block indices in the Z direction, if you want to increase it by going down, okay? Then there are functions of, you could work with these functions and then write an equation for this. Or let's say you have different materials here and you want to assign a different mining, basically cost adjustment factor to them. So in this case, you go with model and instead of, let's say, as you can see here, we have all one. But let's say one of this rock is very competent. It requires more cost for drilling and blasting. Let's say the drillability of the rock is much lower, and it requires higher powder factor to blast it. how I can reflect this? I could put a higher mining adjustment factor for that rock. I could put 1.2, okay? As you could see, there is also something called a rehab cost, which basically when you send this rock to a waste rock dump, and if there is any cost for the treatment and things. So there are many, if you have this information in your block model, you could put these numbers here, and that would basically reflect in the model that you're running. So in this case, we are running, I'll keep it simple, so 1, 1, 1. So, but these are the different things that you could basically play with in order to change the mining cost as in different area of the block. The next one is the processing. Yes?
Can I go back to the mining pad?
Sure.
Let's say this is just like a preliminary slope design.
Yes.
In the real case situation, how do we know what the mining recovery fractions or dilution fractions are?
Very good point. You need to look at the, do some sort of benchmark, okay, for the similar type of deposits in the same kind of situation. What's been, like statistically, what's been the mining recovery and dilution. For example, for gold mines, the dilution is generally depends on the type of gold deposit. If it's a narrow vein gold deposit, generally the dilution is high. Okay, so you need to look at the similar type of deposit and come up with some number.
So let's say down the road, would we have to adjust it based on, like, as we go along then?
Yes, absolutely. Yes, as you have when you have
Like actually start production?
yes, when you have real data, you can easily adjust it. But here at this stage we are doing a feasibility study, right? A conceptual pre-feasibility study, and we try to be as close as possible to real situations. And because we don't have any information yet, so the only thing we could do is looking at existing data sets for benchmarking.
Yeah, it's a good question. It just, so many things in mining are just empirical, right? They still are, right?
That's right.
It's still, it's still like, it's fundamentally, it's not that much different from, when the Romans and the Monies were mining, whatever, right? It's just, it rules of thumb, right? A lot of times we still rely on that.
Correct. Specifically at this stage, right? If it was an underground mine, of course, the dilution could have been, even more. Like in certain underground mines, you see dilutions, 60% dilution for a narrow vein deposit. So processing, there are different things you could select here. One, the two upper one we generally select. Doesn't matter which one you select if you have only one element, okay, or one processing method. If you have different processing method, for example, if you have a mill and a heap leach facility, then it's better to go with the cutoff rather than cash flow. So I suggest that you go always with cash flow. Cash flow allows you to basically will define the ore if it generate a positive value, positive cash flow. So then go with this, and here you need to enter this information. You click on add, and then it's going to ask you what kind of processing method you have. Let's assume that it's a mill, okay? It could be a heap leach, it could be any kind of processing method. Then it's going to ask you for the processing cost, okay? So the processing cost, you could put a single processing cost, or again, it could be a function, okay? How it could be a function? Have you seen metallurgical test? You passed the mineral processing course? Okay, so you probably, I'm happy that you did. So you have seen the recovery and what we call grade, right?
Right.
Grade recovery graph.
Yeah.
Okay, so grade recovery graph is something like this, correct? Right, as the grade of material we are sending to the mill increase, so the recovery is also increasing. right? So it might not start from zero, it might start maybe from somewhere like this, and it gets stable as we, like after a certain grade degree, right? So you could, if you have, for your project, you already have significant number of tests that shows this graph, this relationship between grade and recovery, then you could basically put the recovery as a function of your grade. So every block that's going to be extracted, then the recovery of that block is going to be a function of the grade of that block. Okay, so the same thing for cost. Here, instead of putting a single number for the basically cost of processing a block, you could have it as a function of different things. For example, what could influence the processing cost of a rock?
The hardness of the
rock. Why? It's going to significantly influence the cost of comminution, grinding, crushing. What else is going to influence?
Bad minerals like arsenic.
Presence of deleterious elements, right? So then you could put penalties there. So this is possible to put functions here and make it more complex. Or you could, if you have already, and this is the new, I could say, new area of research also in mining, which is called geometallurgy, and we are trying to put more and more information in the block models that we are creating by better characterizing the comminution behavior of the rock and making these block models basically multi-parametric block models, not just grade, not just density, but put them more information in the block models, like crushability, grindability, recovery, okay, percentage of deleterious element, the cost of putting them in the waste rock dump, how much sulfur it has, okay, does it gonna generate acid, okay, so these kind of things in the block model. And if we do this, then we could do much better here in terms of the mine planning and design. Okay, so let's hear for this example, we go simple, $10 for example, and I could have it different parameters for different rocks. Okay, as you could see, now I'm selecting this for this rock type. And in terms of recovery, as I mentioned, the recovery could be a function of the grade. Okay, could be a function of the grade, or I could put a single number here, 9, okay, 90%. Then, as you could see here, this is I could have costs or penalties for deleterious elements. Here I don't have it. As you can see, the only element I have in my block model is gold, and that's how it's been shown. If I had arsenic, for example, in my block model, I could say, okay, if the percentage of arsenic is more than X%, then go and apply a penalty of X dollar to those blocks. So I could go and put this number here as a penalty. But here I don't have, my block model is simple, just gold, and that's it. So now I need to assign the parameters, the cost to other rock types, so I just need to copy. Okay, so instead of 10 for the quartzite, I assume that quartzite is harder, so I put it $12 for the quartzite, and okay, and again I select, copy, and for the oxide zone I put it $11. I assume that the recovery of all of them is the same. Okay. Again, you could see that similar like the mining costs, you could have cost adjustment factors for processing if you have more information for the processing of each one of those rock types or based on the deleterious elements and things, you could also assign them here if it's already exists in your block model. If you already have them in your block model, you would do it here. Then the next one is the selling. So selling, you need to know the price of the commodity. And this is something you need to come up with basically using all those techniques that you learned from Larry's presentation, if you learned anything. So then you will apply. Hopefully you learn. So long term, for example, 5 years average, or 3 years average, or or consensus. Yes.
Spot price.
Spot price, exactly. So.
Is Larry's slide going to be posted?
Yeah, we will post them. Yes, definitely. I will ask him to send the slide. So this is. So you put a number here. Let's put some simple number here. Let's say $1,000. Then there is selling cost. What's selling cost? Is the cost of transportation of the concentrate or the final material to the port, or any cost related to the selling of the material, or
Insurance and freight.
yes, or if you pay any kind of royalties and things.
Right.
So let's put some number here. I put $35, and then per what? Per troy ounce, right? $1,000 per troy ounce is the price, and the cost is $35 per troy ounce. Then the next one is optimization. Here, it's by default, it's going to do a full optimization. That's what you want. It's going to take the whole block model, including the air, and the way it's going to do it is going to do it based on applying this range of revenue factor, which, as you could see, this revenue factor is changing from 0.3 to 2. What is this revenue factor? So this is a coefficient that's going to apply to your price, okay, and is going to generate a pitch shell based on that specific price. For example, now we choose the price of commodity as $1,000, and as you could see, this coefficient is changing between 0.3 to 2. So if it will start with 0.3. 0.3 times 1,000 is going to be $300. So it's the first thing it's going to do is we're going to use the Lurch-Grossman algorithm to create a pitch shell with the price of $300. So it's going to, obviously it's going to be a smaller pitch shell, but so then it's going to change it to a bigger number than 0.3, either 0.4 or 0.35, whatever, depending on the basically factors, number of factors that you've selected. It's going to generate 86 factors for you, or 86 pitch shells for you with different coefficients. Okay? It's ranging from 0.3 to 2. Why we go more than 1?
In case the price is more than we thought.
In case the price goes to up to $2,000, how the pitch shell is going to expand, okay? Yes?
I've seen in Whittle before that if you use a low factor, it'll mine out one area and then it'll mine out somewhere else as well, because that's where there's good grade. So
yes.
What do we do in that case? Do we just
you need to look at it. So I suggest that for the first shot, go with the default numbers, and then look at your pit by pit graph and see how the pit shells have been created. If they make sense, then keep it there. If not, you could play with this coefficients. Okay. You could change the range to from what, for example, sometimes let's say with 0.3, might not be able even to find any pit,
Right.
okay? Because there's nothing that's going to be economically feasible to be extracted with $300.
Now is that 0.3 to 2.0 the default?
Yes,
Or
default
up-
is this. Yes, by
yeah,
default,
okay,
generally it's ranging between 0.3 to 2. which basically it's start from 0.3 and gradually increase until it reaches to 2, and it's going to generate 86 pitch shells. Nest, we call them, you remember, nested pitch shells. Why we need this? Why we need to generate all those different pitch shells?
To see which one would be closest to today's price and then use the smaller ones for possibly scheduling.
Exactly. So you should to take the one that is close to the today's price as the one that you want to reach to that, and those that are within that pitch shell, smaller ones, as your phases or your expansion phases.
Right, okay.
So then there are other basically icons here that are for advanced applications, like if you have like some sort of physical constraints or you want. So we don't discuss them here, but if you when I'm teaching a graduate level course that's open for also for 4th year students. But I generally take not more than 8 students in the course because you only have 8 advanced bundles of Whittle. And in that course, we are talking about those, advanced options like stockpiling and things, so which we are not talking about them here. So because we don't have time. So we collect. We don't touch this advanced icon. So we just select accept. Okay. So yes, and then we run it. So what's going to do is going to start with this low coefficient number. We'll apply it to the price. We'll generate the first pitch shell, then the second, the third, and etc.
How long does this usually take?
Depends on the size of the block model. If you have a very big block model, it might take hours. In this case, it's gonna be probably around 1 minute for this one.
It also depends on the computer.
It also depends on the computer, obviously, yes. So now we have the results. We could look at the output. So as you could see, these are all the pitch shells that's been generated. Only 72 pitch shells have been created. Why? I will tell you why. So started with 0.3 as the first one. As you could see, actually it made a pit for 0.3. So with $300, you still have a pit shell. And this pit shell contains 19 million ton of rock and only takes, start from the block 44, from surface to minimum bench is 32. It means how many benches you have? Almost 12, right?
Yeah.
As you could see, we see the gold grade here as well. So 1.26, as you could see. Then, if we go down, we see that this is the one, okay? The revenue factor 1 represent what? Represent today's price, okay? Represent today's price. And this is the pitch shell that we want to reach. And as you could see, the total tonnage of rock is about 80 million ton. Okay, this is the total tonnage of ore, the stripping ratio, and the bottom of the pit. Okay, you may see that some of those revenue factors, for example, 1.28 and 1.32, they have been listed together. And why? Because between 1.28 and 1.32, it's going to give you exactly the same result. The pitch shells is not going to change too much. Okay, the same. So that this is, you see that there are different examples here. So that's why it couldn't generate 86 pitch shells, but less than that. Okay, so how many? 72 has been generated. Now, can we look at the pitch shells? Yes, the answer is yes, and we will go and look at the pitch shells. Oops. Okay, so this is the pitch shell number 1. So this is how it looked like. Okay, now I can go to the other, look at the other pitch shells, 2, 3, and the final one. What was the pitch shell with revenue factor 1? Is pitch shell number 36. Okay? So if I look at pitch shell number 36, so this is pitch shell number 36. As you could see, part of the pitch shell has been basically cut. Why? Because the block wall is not large enough, okay, to cover the whole area. But you see the slope angles now for the different walls we have, and this is the pitch shell that we want to bake at the end of the mine life, right? Now, the final pitch shell is 72, and it's going to be very big, right? So this is how, if the price of commodity goes beyond about $2,000. So let's go back to 36. Now we can visualize the different information here. For example, as you could see, this is the block survey. The grades, gold grade. If I go with block survey and I look at the XY section, so all this brown, if I look at the legend, all the brown is the waste, yellow is the mineralized rock, okay, and the blue is something on top, which I don't see it at this stage, okay. So if I go back here and look at so this is the bottom of the pit shell. As you can see, I have the mineralized zone, right? So if I go up, now I have pit shell, but surrounded with all this waste, correct? And it exactly follows the
That's cool.
the mineralized zone. So this is the yellow surface, right? The same thing I could do with if I go and visualize the gold, right? So this is this blocks that has gold grade, okay? And I can, if I go and look at the legend, this is the range of the grade. So the legend. So the maximum, the red is the highest grade, and the blue is dark blue is the zero or barren. So I go down. You can see these high grade spots here, and how the mineralization zone is changing as I go down. So this is good for visualization and understanding how basically the pit shell has been developed. So now we have this this output and report here. So the next step is going to be the operational scenarios, and in the operational scenarios, I will have exactly the same information that I had in the pit shell, as you could see, mining, processing, selling, and the exactly same number is going to repeat here. But as you could see, there is time here. So we are going to consider the effect of time or the time value of money here. Why? Because yes, you have this pit shell that's the final pit shell that you want to achieve, but you can't extract it in 1 year, right? It's going to take time to get to that point. So if you want to change any of those cost or price factors by time, you could do that. For example, I want to have the mining cost for the first few years, for first 3 years as 2.4, but later on, after year 3, I want to decrease the mining cost. Why? Because I'm gonna buy more equipment, and that's gonna reduce with the more equipment. I'm gonna produce more material in lower cost. So then I could basically add another period, let's say period 4, and then the cost is gonna drop to $2. Okay, so I could do this kind of steps here in order to be able to take into account the variation of the cost during the life of mine.
All right, are we good?
The same thing for processing, okay? So if you know that the processing cost is going to change during the time, or recovery, for example, the first few years you have lower recovery, and then after a certain year you get a better recovery, so you can basically put them here as different periods. The same thing for selling, you could write basically the whole, you know, what's your expectation for next few years, and change the price. There are, again, advanced options like stockpiling low-grade material and taking them, sending them to the mill at the end of the mine life. Why? Because you want to send high-grade materials at the beginning and keep all those low grades for the end, because you want to basically have a shorter period of basically return. There are two other important things that you need to enter. One is called time cost, and the other one is limit here. So time cost, the thing that you are going to enter here is the capital cost of the project. The capital cost of the project. So if I put, let's say, 200 million. So is it correct? 1, 2, 3. So 200 million. Now, how you are going to determine this? Again, it's going to be based on benchmarking or looking at these Western Mining Handbook, looking at your operation, how much you are going to produce, and then there are some guidelines that will help you to find basically the first estimate for your capital cost. Terminal value, you know about terminal value, right? What's terminal value?
How much the mine is going to cost at the very end, though?
At the end, when you close the mine, do you have any equipment and things to sell and
salvage,
yes,
like
salvage value? Yes. Replacement capital costs. Replacement capital cost is something when you have something called sustaining capital, right? And you are going to replace your fleet every 5 years or every 6 years. Okay, that's going to be significant big capital cost to put it here. And then you could put it, let's say, every 5 years, every 6 years. Okay. And then the discount rate here. Again, for the discount rate, you are going to find what's going to be an appropriate discount rate for your project, based on the level of study, based on the type of commodity, location of the project, and considering all these factors. For limits, I have to decide what's going to be the mining limit in terms of how much, what will be the size of fleet and equipment I'm going to buy, and what would be the capacity of this. If I put, let's say, 15 million tons.
Would that be maybe because you have a specified tailings storage, for example, and you couldn't increase production beyond that point even if you wanted to?
That might be one of the factors, but
Yeah, okay.
there might be
Yes.
all this
Just
at the beginning.
Okay.
Yes, at the beginning you just go with let's say how much what's your resource and how much you want to produce in terms of the yearly production to basic to get to a reasonable life of
Right,
mine.
okay, right.
You don't want to a very long life
Right.
of mine and very short life of mine. Okay?
Right.
So you want to go with something reasonable life of mine. So what we had in terms of the tonnage was 80 million, if I'm not mistaken. So in the if we go back here for the pit shell with revenue factor 1, we had 80 million, right? 80 million material. So when I'm putting here as limit as 15 million, so it's gonna be something about 6-7 years of operation or a little bit more. So the other one is the processing limit. Okay, so you are going to build a mill in the area. So what's the capacity of this mill?
Right.
Okay, so let's put something like
Yeah.
6 million. Why I put 6 million? If you look at the stripping ratio we had, was about something about 2 point something. Okay, that's why I put this limit to be kind of reasonable with the mining limit that we have. You could only go and select just the mill capacity, and leave the mining capacity as something flexible. Okay, and or to be adjusted with the mill capacity. But the mill capacity, you need to assign a certain mill capacity, and you can change it during the life of mine. You could say, for the first few years, my mill capacity is 4 million ton, 3 million ton. Year 1, year 2 is 5 million ton. Year 1 is 3 million ton. Year 2 is 4 million ton, and year 3 is 6 million ton. Why that might happen? You have heard about the ramp-up period in any of the courses that you have taken?
Production.
Production ramp-up. Okay, so there's something called production ramp-up. When a project starts, there are still things needs to be fixed, so that's why the mill is not working in full capacity. And it may take 1, 2, sometimes 3 years to reach to its maximum capacity. And then you could actually show it here. You could reflect it here by just going and selecting different limits for different period of time. Here, element limit. If you have, let's say, based on a contract, you need to produce a certain amount of gold from this mine and produce it, and then this is going to be your limit, so you could put it here. Okay? But it's rare that we could have something like this. So we go with, again, don't forget to put this unit right as exactly the unit that you have in the selling trials. And that's all you need for the stake. You click accept and you run it. It's going to be just a check mark because it's going to check all these parameters are entered and no calculations required at this stage. Then the next important graph that needs to be produced is called pit by pit graph. Okay, the pit by pit graph is going to show you all those pit shells that's been generated with all these constraints that you have introduced. Okay, so when we click on this, so first don't change anything here and just click run. We had the same error on the, and I think this is the license problem. And because I checked this morning, we had the same error on Tuesday, and
What do the messages say?
yeah, we checked here. It looks like 70% have been defined so far.
What if you put a fixed lead of 1 or 2 in the schedule?
No, nothing is going to change. I've tried this as 1. Still.
Troubleshooting Whittle is
No. Yeah, I need to contact Rock Science, the Jovia, and ask them to have a look at this because I have a dongle-based license and I just looked at it and it was running with no problem this morning. And now with the network license, it's showing this error. We'll fix this and we'll make an announcement about that by as soon as it's solved. So what we'll have? Do you want to open the video that we just posted? Can you show one of the videos? So I will show you the videos and I'll talk on the videos. If you go to the same, yeah, just here, probably maybe number 4 or this number 6. can we bring it? No, it seems to be, we need to go to, so this is exactly the same example that I'm showing it. It was done 2 years ago. Wow. So as you can see, these are all very basic things that you have already learned in mineral economics and the cash flow analysis. Yeah, as you could see, the production rate could influence the maximum MPV. So that's why this limits that we introduced needs to be changed in order to find the optimum production limit that you scenario. So these are the limits that we introduce here. Different numbers have been introduced here. Yeah, probably we need to go to the other one. Okay, so let me bring this. So you already know about the best case scenario, the worst case scenario, in terms of the production scheduling. So the best case scenario is when you basically go and extract the pit shell, the final pit shell by shell. And the worst case scenario is when you're extracting it bench by bench, correct? So here it's actually explaining this this case where the pit by pit graph have been generated, and then so as you can see, this is the graph that's been generated. The pit by pit graph has different three colors. So one is blue, the other one is red, and there's also a green one. The y-axis here is value, or the MPV. The second y-axis is the tonnage, and the x-axis is the pit. So each one of these basically bar charts are representing one of the pit shells that's been generated. Okay. So what you will need here from this graph is you will look at the blue chart and you will select the pit shell that's giving you the maximum MPV, which is generally the one that has the revenue factor 1. Okay. And once you selected this one, also this graph is going to help you to find your basically pushbacks. Pushbacks will be selected based on where you see a jump in the amount of material between two adjacent pit shells. Okay, for example, if you look at this one, there's a big jump between 9 and 10. Okay, so it's better to keep 9 as one of your pushbacks. Why? Because if you start, when the 10 will start, there will be a big pushback. Okay, so that's why we keep in 9, and then the 10, when if we go back to the graph here, so this could be 9, could be one of them. Then you look at again any kind of jump, and you stop in the pit shell before the jump happening. That could be also your basically intermediate pit shells. Why you need this? So if this is your final pit shell that you want to extract, so you need to come up with some sort of starter pit at the beginning. So what would be the starter pit to start, and then you need to make 2 or 3 different phases, okay, before you reach to the final pit shell. So this is going to be the starter pit, okay. Then your first pushback is this. Your second pushback is this. And your third pushback is this. But you need to tell to the software which pit shells have been selected for starter pit, for first pushback, second pushback, and for your economic pit shell. You know the economic pit shell is the one that has a revenue factor equal to 1, almost equal to 1, right? So this is your pit shell that has, which one was that? 36 in our example. So the one that we want to reach to that is 36. Now, this graph will help you to find these intermediate stages, okay? For example, this one could be 5, 9, 19, and then 36, okay? So once you found this, then you could basically enter this information into, let me see if I can. If I go back here, once we run this pit by pit graph, then the next node is this new scheduling graph, where you will say, okay, I want to find the production scheduling for my specified pit shell, which is here the pit shell number 36. These are the different scheduling algorithm, which he's talking about them in this video actually. So we'll talk about them later. So and here is the pushbacks that you need to select. You click add. So the pit shell number that's been selected as pushbacks 5, 9, 19, and 36. So these are the 4 pit shells that I need to make my phases. So the first one is going to be the starter pit, then first pushback, second pushback, third pushback. So by clicking OK, it's going to appear here, and then you just accept and you run it. you accept, and you run it, and it's going to generate. So it's not going to run because the previous one has failed to run. So that's what. But the result will be something like now he's actually doing this. So once the pit by pit graph was. He's talking about this, selecting this. So 35 has been selected as the specified case, and he chose a fixed lead of 3. So it's the algorithm that's going to use for the planning. And he explained all these 3 algorithms: fixed lead, Milava balance, and Milava NPV in this presentation. So he's now entering those pushbacks. As you can see, 5, 9, 19, and 35 has been selected. And now now you have all these outputs. If you look at that, so this is the output. As you could see, so it's going to be something like a bar chart, which has the production in different years. If I can stop it. So the production planning will be something like this, where you have year in the x-axis, and you have the tonnage in the y-axis. So every year will be presented as a bar chart with different color for ore and waste. So year 1, year 2, year 3, year X, the life of mine. It will also give you running this close the Whittle. Okay. So it will also give you all these economic attributes of the project, like IRR, NPV, payback period, tonnage of ore that's going to be extracted, tonnage of waste that's going to be extracted by the end of the mine life, and all those information that you do. The other thing I wanted to show you, so let's see if we can open again the Whittle. So the other thing, once you have those information, the other thing that might be interesting for you at this stage of the project is how you can take one or some of these pit shells and bring them to the visualization software, to mine design software, like Vulkan or other softwares that you are using. Okay, so in order to do this, you just need to go back to this pit shell knot, and you right click on this, and there is option to go and export pit shells as DXF. Okay, so you click on this, and here it's going to ask you which pit shell you want to extract. You want all the pit shells or selected one. So for example, in your case, if you want to have all the phases, 5, 9, 19, and 35 or 36, just write them here, and you say run. So all of them have been already created in the folder that you specified for your Whittle analysis. So it's going to be as a DXF file, and then you can visualize them as a solid in your mind visualization software.
Would gems be suitable for that?
Gems, Swordpack, Vulcan,
Yeah.
all of them.
Yeah. Gems is the one we know now, so I mean.
Yeah, you
Yeah.
can absolutely use it. Yeah.
Sure.
That's all you need. Yes.
You know how there was